Welcome everybody to the webinar of today. The speaker of today is Zhouyang Ge, and he's going to talk about rheology of periodically sheared suspensions undergoing reversible-irreversible transition. As usual, I introduce the speaker very briefly and then I give him the floor. So Zhouyang Ge is a postdoc in fluid mechanics at the University of British Columbia in Vancouver, Canada. He obtained his PhD degree in 2020 from the KTH Royal Institute of Technology in Stockholm, Sweden, and was a recipient of the 2019 Tetra Pak Award in computational fluid dynamics from the Swedish National Committee of Mechanics. Zhouyang is interested in fluid problems, especially when droplets of particles are involved, and currently his research focuses on modeling hydrodynamic interactions between individual particles and understanding their effect on the collective dynamics and mechanical properties of particle suspensions. So it's with great pleasure that we have here today Zhouyang Ge, and I now stop sharing my screen. Anthony, I invite you to share your screen then, and you can start.
Here's my screen.
Yes.
Okay, thank you, Francesco, for the introduction, and thanks for inviting me. Today, I would like to talk about the rheology of periodically sheared suspensions undergoing reversible-irreversible transition. But before I start, let me acknowledge the people who have guided me or contributed to the work. I started working on suspensions with Professor Luca Brandt at KTH during the last stage of my PhD. We had a long and fruitful collaboration with Professor Mario Minale and his former PhD student Raffaella Matona at the University of Campania in Naples, Italy. After my PhD, I continued to work on denser suspensions and moved to UBC to work with Professor Green Alfring. So the fundings has come from both the Swedish and the Canadian side. Last but not least, I would also like to acknowledge Professor Shervin Bagari for hosting me during my current postdoc stay at KTH. So this is our agenda today. I will first motivate why periodically sheared suspensions are interesting and why do we want to study that, followed by a brief discussion of the numerical methods, and then a more extensive discussion on the results. So let's get started. We know that no Reynolds number flows are governed by the incompressible Stokes equations. And because Stokes equations are linear and depend only on the boundary conditions, Stokes flow are kinematically reversible. This is famously demonstrated by G.I. Taylor in the 60s. In the pictures on the bottom, here you see two concentric cylinders with viscous fluids between them. And on the interface of the viscous fluids, Taylor wrote the expression R much less than 1, and then he rotates one of the cylinders forward. You see the expression disappeared, but only to reappear when later the motion was reversed. Clearly, this shows that the fluids between the cylinders did not mix. The motion is completely reversible. And naively, you would think this is the same when you increase the size of the particles. But it is not. In the 70s, researchers began to measure the particle dynamics in simple shear flows more accurately. And what they found is the particles diffuse, they mix. Now, mixing means when there is a loss of correlation, which means that if you reverse the boundary condition after some time, the particle will not return to the original position. They should, which means if you reverse the boundary condition, the dynamics will not reverse. And this has led some researchers to call suspensions fluids with fading memories. Now, the question now is to understand this. Given that the underlying flow is Stokean and is reversible, how to understand the irreversible behavior of the particle dynamics? Researchers have proposed that there may be some noise in the system, such as Brownian motion, and there may be imperfections on the particle surface that they are rough, and the particle dynamics may be sensitive to these details. And that is why when these papers appeared and showed that the particle dynamics is chaotic, it makes total sense. What this authors did was to use numerical simulations to simulate a number of almost identical initial conditions, but with a slight difference. They let the simulation evolve and then measure the distance in the phase space spanned by all the particle coordinates. And they found that the distance between the different pairs of simulations increase. Now, if the dynamics are chaotic, this distance should increase exponentially fast in time. Here we see the distance measured as time, and the y scale is logarithmic. So here is exponential, which means the dynamics is chaotic. And this explains why the particle motions are irreversible, because there's always some noise in experimental systems. So when you reverse a boundary motion, it will not return to the original state. This seems to explain the experimental observations. However, the story didn't end there. A few years later, Pine and co-workers did more accurate experiments. They kind of repeated Taylor's classical demonstration in a more quantitative manner. So here we see a Taylor-Couret cell. The researchers then put suspension into this geometry. They can shear the rheometer back and forth, and then through particle tracking techniques, they can measure the particle displacement periodically. So the procedure is you start with any initial conditions, you move one of the cylinder forward, backwards, and then you measure the particle positions, and you repeat this. So if the particle dynamics are completely reversible, then they should appear dots in this periodic checking. However, what the researchers found that the particle exhibit apparent anisotropic random walk, which means that the dynamics is diffusive, as would be expected from the chaotic behavior. But this diffusive behavior is only there when the strain amplitude is above a certain threshold. Here, the strain amplitude is defined as the distance traveled by one of the cylinders divided by the gap of the two cylinders. So it is a measure of the dimensionless deformation. What the data shows is when the strain amplitude is less than a certain threshold, the diffusivity of the particle is negligible. But once the strain amplitude exceeds that threshold, it becomes measurable. So what the experiment shows, there is a transition between a reversible state and an irreversible state in the particle dynamics. Now, this transition is characterized by a critical strain amplitude. This amplitude does not depend on the size of the particles. It does not depend on how fast you rotate the cylinders. It only depends on the volume fraction of the suspension. Now, this is very surprising. Why should there be a transition in the dynamics? Remember that the previous study have shown the particle dynamics is chaotic. So Pine and co-workers also did simulations to check the chaoticity of this case. And they found that the Lyapunov exponents, which measures the chaoticity, also increased dramatically after the same strain amplitude. And this seems to explain the experimental behavior, because the system becomes much more chaotic after a threshold, then the dynamics becomes much more irreversible. But the question is still, why should there be a threshold there? Why should there be a transition? A few years later, a toy model was proposed trying to answer this question, but this time from a completely different perspective. The model is actually very simple and can be described by this cartoon here on the bottom. So imagine we have a box. Inside there are a few particles. For simplicity, let's say just there are 3 particles. And then you deform the box. The particles will follow the affine motion of the deformation. If the particle is relatively far away from its neighbors, you will just follow the motion and then come back when you reverse the boundary conditions. So if you were to check the position periodically, the particles will not move. However, sometimes 2 particles may get very close to each other. So when you shear the box, they may collide. And if particles are colliding, it's reasonable to assume that they may not return to the original position when you reverse the motion. And the simple way to model this effect is to give them a random kick, as illustrated by the arrows here. And this is a unicycle. Then you can repeat this indefinitely to model the particle dynamics, to simulate the particle dynamics. And here comes a remarkable observation. If the strain amplitude, that is a dimensionless deformation of the box, exceeds a critical value, there will always be some dynamics. So here, this plot shows a fraction of particles that are colliding with each other. You see, initially, it is a very high value, around 0.6. As you start shear this back and forth, it reduces a little bit, but it stabilizes at a finite value. And this value depends on how big the volume, the strain amplitude is. However, if the strain amplitude is below a threshold, the particle initially have some dynamics, then eventually they will self-organize into a special configuration that avoids future dynamics, and all the collisions will stop. And this is called, and this special state shown by this blue curve is called an absorbing state, and this transition is called an absorbing state transition. This transition is characterized by a critical strain amplitude, as you can see here, and it only depends on the kinematics of the deformation. So this is a very simple model. You only have two ingredients. That is, one is the excluded volume interaction, and the second is noise. And it seems to explain the dynamics. It's very elegant. However, hydrodynamic interactions here are completely disregarded, which were what people think are very important. So the objective of this study was to test the effect of hydrodynamic interactions on the emergent dynamics. The reason we want to test that is we know that hydrodynamic interactions are always present in experiments, but the previous simulations often simplify that. And here I mentioned the hydrodynamic interaction as many Birdie versus pairwise. This is purely a numerical decomposition that we do. In reality, the hydrodynamic interaction is of course continuous, but by separating them into these two parts allow us to simulate them much more efficiently. So this is something I want to mention first. That's our first objective, to test the effect of hydrodynamic interactions. And the second objective is to examine the rheological response of periodically sheared suspensions undergoing reversible-irreversible transition. We want to test that because we know rheology depends on the microstructure, which means how the particles are arranged. And this microstructure depends on the dynamics, the detailed dynamics, which in turn should depend on the hydrodynamic interactions. So by including the effect of hydrodynamic interactions, we should be able to get the rheology response. And also we know that sometimes the suspension can have very strange rheology. It can have redependence, which simple models cannot produce. So we want to test that with our model. This is the second objective. And the final objective is what we really want in the end is to have a better understanding of the connection between the emergent dynamics of the suspension and its rheology. So these are the three objectives of what I want to show in this study. And then I will just briefly mention the numerical method. So for a dense particle suspension, the governing equation is the non-Zhouyang equation. Here, U is the velocity of the particles, V is the potential, interparticle potential between the particles. C here is a resistance tensor. Effectively, this gives you a drag force. In the most simple case, C can be considered as a scalar, which would be the drag coefficient. But in general, at no Reynolds number, this is a tensor that depends on the position of all the particles. And the last term, zeta, is a noise term that you have that are not modeled otherwise. In the overdamped and non-colloidal regime, that is, if we neglect the inertial term on the left-hand side and the noise term on the right-hand side, the velocity can be written as the inverse of the resistance tensor multiplied by the force. Here we can do the inverse because the resistance tensor is symmetric and positive definite, and it only depends on the particle microstructure, which means this resistance tensor encodes all the hydrodynamic directions. So what we want is to find a method that can efficiently evaluate this equation, evaluate the resistance tensor, then give us the velocity of the particles, then we can update the dynamics. We use a method called Stokesian dynamics to approximate the resistance tensor for suspensions of finite size and hydrodynamically interacting particles. The main idea is to do a multiple expansion for the far-field many-body interactions and combine that with the exact solution for near-field pairwise lubrication. The theoretical basis is the boundary integral expression for the Stokes flow around particles and Foxian's law that we can use to relate the fluid flow to the particle velocities. The final solution, neglecting the Brownian motion, can be written as such. This is the particle velocity is equal to U infinity, denoting the velocity of the flow in the absence of the particle, plus the deviation term, which can be written as the inverse of this force velocity coupling resistance tensor times all the forces. Here, Fp denotes all the interparticle force, and this E infinity term denotes force due to the stringing motion of the flow. And we use a method called fast Stokesian dynamics to solve the previous equation. On a glance, it may look like we're making the equation more complicated. Previously, just 1, now we have this more complicated expression. But this by rewriting the equation in this way, actually, we can gain a lot of computational efficiency. I will not go into the detail of the method. The algorithm was written in Fioro and the Swan 2019 JFM. We take their code and we validated and did a little bit of debugging. So the essence, the main thing, the main advantage of the code is that it's by writing the equation into this way, we can solve the equation very efficiently using iterative methods such as GMRS. And the original author have proposed a very efficient preconditioner for this problem. And this solver is implemented as a plugin to an open source MD software, which has GPU accelerations, which gives a numerical performance of log n, which is really fast. And we open sourced the source code, and also we have a simplified version of the code without long-range hydrodynamic interactions, which are also available. And just to show that the code is correct, we have validated the code for two particles in shear flow against a theoretical analytical solution by Batchelor and Green. Here we're comparing the trajectories of the two particles as they're passing each other. This is the angular velocity of the two particles. Both agree exactly with the theoretical solution. We have also tested the suspensions, the rheology of a dense suspension, here comparing with previous simulations and also with empirical fit. Overall, we have a good agreement with previous results, so we can proceed with our simulations. So now let me briefly describe the setup before we discuss the results. We're considering periodically sheared suspensions. There's a lot of particles. We consider minimum of 500 particles, and we also check 4,000 particles to see if there's any size effect. And we consider 3 volume fractions, 30, 40, 50%, subject to least Edwards boundary conditions, which is a standard boundary condition for shear flows. The particles interact not just hydrodynamically, but also through non-hydrodynamic forces. The standard forces are electrostatic repulsion or van der Waals attraction. Here they have these specific forms. We will not discuss the detailed choice of the parameters here. They are chosen because we have validated this code in previous cases. But if you want to reproduce one specific experiments, these are basically where you can tune the knobs to change the parameters so that you agree with the experiments. But in this study, we are more interested in the qualitative behavior, so we do not change these parameters. The most important part is the external shear that's being imposed. That depends on the time. And here is a sinusoidal function of time. This introduces 2 control parameters. One is the strain amplitude, gamma naught here. That is how much you deform the suspension. The other is the oscillation frequency. Here is written in the dimensionless form. That tells you how fast you shear the box. So both of these can affect the dynamics and the rheology of the suspension. But the strain amplitude will be the more fundamental control parameter. The oscillation frequency will be there only if we invoke the attraction term. So in the rest of the simulation, in the rest of the talk, I will focus on the first part. That is the control parameter is the strain amplitude. But in the end, if we have time, then we'll discuss when we include the attraction, how the frequency dependence can also arise. I hope that's clear. So now let's look at the results. This slide shows you the particle displacement per cycle for different strain amplitude at different time. So here, each row is a strain amplitude from 0.4, 0.8, 1.6. Each column is different time instant in the unit of cycle. So half cycle, 1 cycle, 4 cycle, 40 cycles. What we see here is there is always some displacement initially, but if the strain amplitude is small enough, eventually they will decay and disappear. If the strain amplitude is above certain values, then the dynamics, the displacement will persist. We observe an anisotropic particle displacement. Here, the anisotropy is interesting, especially in the first half a cycle. We see that it is an oblique, it's tilted. This is due to the particle repulsions. Because when you have 2 particles interact with each other, you shear them. If there's no particle repulsion the displacement should be 0 and symmetric. Due to the particle repulsion, they do not return to the initial position, but they were tilted in one angle. And once you do another half cycle, you tilt it in the opposite angle. And once you repeat this back and forth, you get this anisotropic shape. This is also called Taylor dispersion in simple shear flow. And from those particle displacement, we can calculate the per cycle diffusivity, here defined as the mean square displacement divided by the total accumulated strain over one cycle, as given by this expression here. So here I'm plotting the case for 40% volume fraction, the per cycle diffusivity as a function of the total strain for different amplitudes. Here, strain and time are equivalent. Strain is basically a dimensional version of time. So we see that clearly there are two dynamical regimes, either a decaying dynamics or persistent dynamics, depending on the strain amplitude. Now, if we put the final value of all the D cycle in one plot to show the effect of the strain amplitude, we see that D cycle always increases with amplitude. And it increases particularly fast near an intermediate region. And this intermediate region depends on the volume fraction. It reduces with the volume fraction. So what we're saying is, what we're observing is there is a reversible-irreversible transition. At very small amplitude, the diffusivity is very small, and it increases quickly with the strain amplitude. And one thing to note that is here the region that I marked here is not estimated from this curve because the data is very sparse. We cannot measure where the highest slope reliably, but these are actually estimated from rheological results that we'll show later. So that already gives you an idea. There is a connection between the dynamics and the rheology. There is something special in the middle range where the dynamics transit. But we'll come back to this point and it will become more clear later. So we can put all the results in a phase diagram here as a function of the volume fraction and the strain amplitude. We see that there are two regimes and they're separated by critical strain amplitude. The dashed line here is actually from experimental measurements. It's not our results. So we see clearly there is a good agreement between the simulations and the experiments. The inverse square scaling with the volume fraction here is interesting because it suggests that the particle diffusion is due to many-body scale couplings. Because if we have a particle in a suspension, in homogeneous suspension, the probability of this particle interacting with two other particles will be phi squared. What's perhaps not immediately obvious is that the far-field hydrodynamic interactions are not responsible for this many-body effect. As a result, are similar with or without them. So in this figure that we have seen previously, there are two sets of markers, solid markers and open markers. The solid markers are with the full hydrodynamic interactions. The open ones are without the long-range interactions. And we see they pretty much align on top of each other, which shows that far-field hydrodynamic interactions are not critical for predicting this behavior. What that suggests is the local interactions, including pairwise lubrications and electrostatic repulsions, are sufficient to couple the particle motions to yield the collective dynamics. So we confirm the previous understanding, the previous conjecture that exuvitive volume interactions dominate the particle dynamics. Hydrodynamic interactions are less important here. What about the rheology? As a preliminary, in simple shear flows, the stress tensor has a very simple form. It consists of off-diagonal terms, which are the shear stress that dissipates energy and the diagonal normal stresses that do no work. And by definition, the stress tensor is symmetric and traceless. So the quantity of interest here is the suspension viscosity, which is proportional to the shear stress, and the two normal stress differences, because the normal stress are traceless, so we don't need three. And both of them can be non-dimensionalized in standard ways. And when we have oscillatory shear, the shear rate will be a function of time. And here I impose that as a cosine of time. Because of that, the stresses can then be decomposed in Fourier series, written as such. The response, the rheological response for suspensions is mostly viscous, and they're dominated by the first field harmonics. What do I mean by the response is viscous? if we plot the shear stress together with the shear rate, we say they both oscillate and they're aligned on top of each other, so they're in phase with each other. This is a viscous behavior. If the shear stress is in phase with a strain, then you would have an elastic behavior. And we can also look at the power spectrum, and we see that the harmonics decays very quickly. So we don't need to keep all the terms, just the first few will be enough. So with that, we can first look at the viscous response. And here I'm expanding that with I'm keeping only the first two terms, the eta 1' and the eta 3'. Here, there is only the odd terms because viscosity is an odd function of time. If you change direction, the drag should also change directions. So it's an odd function. So we only need and because it decays very quickly, so we only need the first two. And the first term eta 1' is the average viscosity per cycle. And then we can compute that for different strain amplitudes at different volume fractions. And they're plotted in this figure on the left. What we see is there is a non-monotonic relationship between the eta 1' and the gamma naught. And there is a minimum near the intermediate region of the strain amplitude. So it's a little bit complicated in the plot, so let me unpack that for you. First, we see that if we were to look at the red plot at the 40% volume fractions, when we increase the amplitude, we see the average viscosity per cycle first reduce and then increase. This is also the case for 30% volume fractions, and it's the case for 50% volume fractions. Here, there is two branches. In this case, it doesn't go up because this case corresponds to the monodispersed suspensions, which tends to crystallize at high volume fractions on the large amplitudes. So, but that is an ideal situation. In reality, there is always some size disparity. And once we introduce that, we do see there's also a non-monotonic behavior at around the same region, with a minimum value at around the same region. So what this shows is there is a reduced viscosity near an intermediate amplitude. Now, how do we understand that? The reduction from the high amplitude side, so if we were to reduce the amplitude from a very large value, can be understood from classical experiments on shear reversal, shown on the right. So in the 80s, people have done experiments with a suspension in a simple shear. They measure the viscosity, steady-state viscosity, and normalize to be 1. And then if all of a sudden they reverse the direction 180 degrees and shear it backwards, they observe there's a sudden drop of the shear stress, followed by continuously drop and then gradually increase. So what this shows is suspension is an anisotropic fluid when being sheared. So when you reduce the strain amplitude, the viscosity that are being experienced here will be less than if you have a large amplitude. That explains why there is a drop from the large amplitude side. Now, why there is also a drop from the small amplitude side when you increase the strain amplitude? This is more subtle, and it involves a history effect, as we have seen earlier. The dynamics has an absorbing state transition. So this I will come back later. At the moment, it's enough to know that there is a reduced viscosity near the critical amplitude gamma c. Then we can look at the third harmonic, which measures the intracycle shear thinning or thickening. How is that related? To see that, we need to do a few simple algebra. Let x equal cosine of omega t, and the t here is from nt to n plus 1t, so t is within a cycle. Then from trigonometry, we know that cosine 3 omega t can be written as x in this way. Then we can plug in this into the original expression for the viscosity. With some rearrangement, we get an expression like so. So the instantaneous viscosity can be written as x times eta 1', which we know is average viscosity per cycle, plus a correction term, delta x. And this correction term is proportional to a quadratic function that I plotted here. So if this eta 3' is positive, then this correction will be higher when x is bigger. And we know this x is essentially the shear rate. So then if eta 3' is positive, then this will be shear thickening, because this correction term is increasing. And if eta 3' is negative, it will be shear thinning. And our data shows that the suspension is almost always shear thinning, because here I'm plotting the negative at a 3'. So we see it's always shear thinning. And furthermore, the shear thinning effect is enhanced near an intermediate region corresponding to the critical strain amplitude, as we can see here. So this is our second signature. There's enhanced intracycle shear thinning near the critical amplitude. And I should mention that this argument that the relationship between at the 3' and the shear thinning or thickening was originally proposed by Ewald and co-authors. In their way, they were using Chebyshev polynomials, but essentially the argument is equivalent to what we derive here. So those are the viscosities. What about the normal stress differences? The first normal stress differences measures the difference between the normal stress in the flow direction x and the velocity gradient direction y. So if there's more tension in the flow direction or more pressure in the velocity gradient direction, you will get a positive N1 and vice versa. What we're seeing here is N1 is practically negligible for small amplitude, and then it becomes negative for large amplitude. The small amplitude side can be understood from the microstructure, which we see here are symmetric, symmetric. So there's equal amount of tension and pressure in both directions. They cancel out, so it's negligible. This is called in the literature purely hydrodynamic limit when there's no collision. The N1 in the large amplitude side is negative because the microstructure is anisotropic, and as we can see here, so there is more collision in the flow direction that would contribute to a pressure that would make N1 negative. And this is also observed experimentally. So this is a standard observation. But what's interesting is perhaps there is a region that N1 is slightly positive before it turns negative. This has been pointed out in previous experiments, but they didn't, because the experiment cannot really measure where this effect comes from. They did not know whether this is due to hydrodynamics or due to particle collision. Here with our data, we show that the hydrodynamic contribution is always negative. So this positive part has to come from collision. So that would answer the previous question. However, this positive N1 here is very weak. So we cannot expect this to be a robust signature of reversible-irreversible transition. So this is a minor point. Now let's move on to N2, which is a more interesting part here. Similar to N1, N2 measures the normal stress difference in the velocity gradient direction y and the vorticity direction z. And we can decompose that also in Fourier series. The normal stress, by the way, is an even function of time. So we only have the 0, 2, 4, 6, etc., all the even terms. First, let's look at the average response at nu naught. We see that it is negligible for very small amplitude, and then all of a sudden it becomes negative, because here I'm again plotting the negative nu2. So it's negligible N2 for small amplitude, and then very negative N2 for large amplitude. We know that N2, we know the particles, when they're being sheared, they tend to collide in the shear plane. So there will be a lot of negative contributions from the y direction, and there's not so much collision in the z direction comparing to y. So that's why N2 would be negative for the large regions. And also in this plot, we also have two sets of markers for each point. The empty ones are without hydrodynamic interaction, are the contribution from the collision, sorry. So, and they overlap with our observation here. So that confirms the negative N2 is due to particle collisions. And this is what we expect. We know that at a very large amplitude, the particle collides, that contributes, that makes N2 negative. And at the very small ones, they organize into absorbing state, they don't collide, and then N2 is practically 0. Then we can also measure the ratio of the fourth and second harmonics, which would give us the relative effect of the two nonlinear terms. And this is very surprising. What we found is this ratio nu2 over nu4 over nu2 completely change order at the intermediate region. So for very small amplitude and very large amplitude, we see that nu4 is much smaller than nu2. So essentially, the the suspension is responding with a 2 omega frequency as we share that. However, at the intermediate region, this ratio would flip and nu2 would become dominant. Nu4 would become dominant. So the suspension will respond with a 4 omega frequency. There is a frequency doubling near the intermediate amplitude. And we can also see that from the Lissero curves, if there's a very small amplitude, it goes in this knot shape back and forth, the 2 omega frequency. If this is very big, it goes in this like a very noisy shape, but it's also 2 omega frequency. But at the intermediate region, it goes in this double knot in one side and another double knot in another side. And interestingly, we see that for this for the very small strains, it's first becoming positive, which is different from the previous values. We know that nu2 coming from collision can only be negative. So that suggests that maybe there is a hydrodynamic interactions that contributes to this positive trend. And indeed, it is the case as we see from the inset plot here, which are the contribution from the hydrodynamic interactions alone. So what that shows is this frequency doubling is the effect of the hydrodynamic interactions. And this is perhaps the most strange results, so to speak. I have not seen any experiments showing that, perhaps because it's not easy to measure N2 in a conventional rheolometer, but I think it would be interesting to test this experimentally. So to summarize, we have shown a number of rheological signatures of the reversible-irreversible transition, including reduced viscosity, enhanced intracycle shear thinning, onset of finite second normal stress differences, and frequency doubling near that critical point within a cycle. And we have shown that the suspension dynamics have this reversible-irreversible transition, which are mainly dominated by the non-hydrodynamic interactions. But then the question is still, why should there be such a rheological signature corresponding with this reversible-irreversible transition? I have already explained some of that. In the rest of the talk, I will try to give more ideas for that. And that has to do with the microstructure. So when we have a suspension and disorder material like this, how do we quantify, how do we measure the microstructure? The first thing to do perhaps is to calculate the pair correlation function. For homogeneous and isotropic suspensions, this is very simple. You count the number of particles within a spherical shell from any reference particles. With some proper normalization, you get this oscillatory shape. Each peak here corresponding to one spherical shell because the particles have finite size. They cannot overlap. And the plot on the bottom left here shows results for one specific K at 40% 0.8 amplitude. We see that initially was the dash line, and finally it's shifted slightly to the right, so meaning that the particles slightly getting away from each other. In the previous case, we were assuming the pair correlation is isotropic, which may or may not be the case. To test that, we need to see the angular distribution functions, which are shown here. So these are the angular distribution plotted on the map for different distance. So here is R over A equal to 2.1, 4.2, 6.0. So 0 corresponds to the first three peak in the Rheology distribution function. And the left column is the initial condition, the right column is a final condition. What we're seeing here is initially, I start with something isotropic, it's random, but finally, at the final stage, there is an anisotropic short-range structure within about 10%, within a boundary layer of about 10% of the particle radius, that there's almost no particles in certain regions. And beyond that distance, the particles are again isotropic and disordered and uniformly distributed. So what this shows is there is a depletion of the particle due to shear, due to the repeated shear, that they migrate from the regions where there is a higher probability to collide. Remember, previously in the displacement figures, we have seen there is anisotropic disagreement due to collision. This distribution is the final result of that. The next thing we can check is the nearest neighbor. The reason we want to check nearest neighbor is because viscosity is linked to the forces on the particles, and the forces are bigger if the particles are closer in general, in our case. So here I'm plotting the distance to the case nearest neighbor as a function of the nearest neighbor. So we see that this is the distance to the first nearest neighbor, second nearest neighbor, third, it has to increase. And the blue ones are the initial condition, the orange ones are the final condition, and they're plotted for different strain amplitude. What we're observing is that both the RK, both the distance, and Kc, which corresponds to the crossover between the initial and final neighbor distances, both of them increase with gamma naught in the reversible regime. So meaning that if the gamma naught is smaller than the threshold, increase the gamma naught would push this curve to up and also to the right. And that is why we observe a reduced viscosity as the amplitudes are approaching, as the critical amplitude approached from below. We can also calculate from the nearest neighbor, we can also construct nearest neighbor graphs. So the simplest, so this is probably the simplest way you can use to analyze a disordered system to make them into clusters. So a nearest neighbor graph is defined as a graph made of particles that are connected to its nearest neighbor. So this is not a symmetric operation. And also you have to have two particles in a system to be connected. And the smallest cluster is two. You cannot have an isolated cluster. The results are shown on the figure in the right figure. The top panels are the initial condition. I'm showing the size distribution and the shape factor. The shape factor is defined as the ratio of the largest eigenvector over the smallest eigenvector of any cluster. So each of the shape here, I can assume them to be a rigid structure, and then I can calculate the moment of inertial tensors. And then the ratio of the largest to the smallest moment of inertial tensor, eigenvalues of that will give me the shape factors. So I can also plot the distribution of the shape factors. What we're saying is, as we're sharing the suspension back and forth, in a steady state, all the large clusters disappears. So we see here initially, there's a larger cluster composed of 42 particles. That is almost 10% of the suspension are in one cluster. But eventually, they're all becoming very small cluster, and the most probable one are cluster of size 2, which is to say that there is no clusters in the suspension. They're all like far away from each other. And the shape factor also have a slight shift. This shift can be calculated precisely based on the nearest neighbor's information, which I will not show here, but they are available in the papers. So this gives us some ideas about the microstructure of the suspension. And the key point here is the particles, they separate. Which brings us to the final point here, hyperuniformity. Both the LNG analysis and the uniform increase of the nearest neighbor's distance, RK, at a fixed volume imply suppression of density fluctuation at large length scales. Here, the density fluctuation can be quantified by the variance of the number of particles within a randomly located sphere of radius r. So again, this picture, if we just take a random sphere in a system centered around a particle, and we count how many particles are there, and then we shift this origin of this sphere and we do it again, and then we increase the size, we can calculate the number variance. And the exponent of the scaling law of the number variance with respect to R measures the degrees of hyperuniformity. For a disordered structure such as an ideal fluid, this exponent would be 3 in 3D. For a crystal, there would be 2. A simple physical intuition to understand that is for a fluid, the fluctuation happens inside the volume. So the variance would increase with the volume. But for a crystal, the fluctuation happens on the surface. So the exponent is 2. And anything that's less than 3 is defined as hyperuniform material. And what we're seeing here is we started with 3, and then very quickly it would reduce, and eventually we can extrapolate this exponent to 2. So that is a strong evidence suggesting that the suspension will eventually become hyperuniform. And the reason I'm interested in the hyperuniform material is this structure has been shown to exhibit many interesting properties, such as photonic band gap and some other thermal properties. Here we're showing it can also have interesting rheological behaviors because as we have seen earlier. And also this hyperuniformity has also been confirmed experimentally for periodically sheared colloidal suspension previously. So we are in agreement with those results. So that would conclude the previous part of the study. Now, in the remaining, I would try to briefly mention that when we include attraction force between the particles, it's possible to have a second threshold for the reversible-irreversible transition. The beginning point is a peculiar rheological observation. So our experimental collaborators in Naples did experiments in simple shear and oscillatory shear flows. They found that the suspensions can be shear thinning in oscillatory shear, that is if you shear them periodically, but rate independent in simple shear. So the figure on the left here shows the relative viscosity as a function of the shear rate. The shear rate increased by 3 orders of magnitude, but the relative viscosity is basically constant. However, when you shear the suspension periodically at the same strain amplitude, which is 1% here, but at a different frequency, the complex viscosity would change. In this case, you increase the frequency, the complex viscosity reduces, so it's a shear thinning. This is very peculiar. Why should there be a redependence only in oscillatory shear but not in steady shear? So we want to investigate to try to understand it. And we did simulations, and we tried a few different effects to include in the simulations to see which one could reproduce the experimental observations. And eventually, we found that a very weak van der Waals attraction could qualitatively reproduce experimental observations, which are shown on this figure here. Again, this is a qualitative comparison. So the figures the curves on the bottom are the experimental measurements for different volume fractions. You see they all exhibit this shear thinning, and plotting the viscosity as a function of a shear rate, which is non-dimensionalized. And the simulation also have this behavior, but for steady shear flows, the viscosity is constant around over 3 decades of the shear rate. And because we have the simulations that reproduce the experiment, we can see where this change comes from. So we can look at the stress budget. Surprisingly, the change in the viscosity in the oscillatory shear case did not come from van der Waals attraction, but it's mostly coming from the hydrodynamic directions, as shown by this solid region here, which corresponds to lubrication. So this is interesting. What it means that is the van der Waals interaction is so weak that it doesn't change the viscosity very much, but is strong enough to nudge the microstructure reorganization that changes the hydrodynamic interactions, which give rise to this rheological behavior. And also we can look at the particle dynamics. We found that at a small shear, if the shear rate is small enough, the particles, they tend to collide. Here, this is a fraction of particles that collide with each other. And the inset shows the particle diffusivities. So both of these increase as the shear rate increases. So that means the shear rate below which the shear thinning occurs, in our case, is around 100, defined non-dimensionally, also mark the onset of particle diffusion. This suggests a second omega-dependent, a frequency-dependent threshold for reversible-irreversible transition. Previously, we were showing the transition controlled by the amplitude. So at a given volume fraction here, you increase the amplitude, you go from reversible to irreversible. Here, at a given frequency, you reduce amplitude, you go from reversible to irreversible. And this frequency-dependent amplitude do not depend on the volume fraction. So these two are two independent parameters. So this is a second threshold due to the attraction force for the reversible-irreversible transition. And finally, the reason that there is only rate dependence in oscillatory shear but not in steady shear is due to, I see there's a question from the chat. Okay, sorry. Finally, there is the reason that there is this rate dependence only in oscillatory shear but not in steady shear is due to the time scale of the two effects. The realization time due to attraction is much longer than that due to collision. And we know that the suspension dynamics is dominated by collision in steady shear, and collision do not have a characteristic time scale. Well, the collision is not rate dependent. That's why the rheology is rate independent in steady shear. So in summary, we have shown that periodically sheared suspensions can undergo reversible-irreversible transition characterized by either a volume fraction or frequency-dependent critical strain amplitude. The dynamics are mainly governed by non-hydrodynamic reactions. And there are at least 4 rheological signatures of this transition in terms of the viscosity and second normal stress differences. The rheology is mainly determined from hydrodynamic reactions. Finally, the connection between the rheology and the emergent dynamics lies in the shear-induced microstructure, which tends towards hyperuniform near the field-dependent critical amplitude. With that, I thank you for your patience and attention.
Thank you very much, Anthony, for the talk. And I would say then we can open the floor for questions if you agree. So for whoever would like to ask a question, just feel free to unmute your mic and ask your question.
I don't know if I was going too fast because I cannot see the audience.
Oh, well, I think it was quite well structured. I mean, the presentation was very clear, actually. Well, maybe I can start with a question. The first one is, so what you show is always like monodispersed suspensions, right?
Most of the cases, yeah.
Most of the cases, okay. So this is the code you presented. Is it working for monodispersed, or it can work for polydispersed too? I mean,
yeah. So there are 2 codes. The fast ocean dynamics is only for monodispersed suspensions due to the numerical technique that was employed. It makes the computation much faster. The other one, the lubrication dynamics, are for bidispersed suspensions or any kind of dispersions.
Okay. Okay.
Yeah.
Okay. And except for the crystallization phenomenon, you said it before that evidently it's strongly related to monodispersed suspensions. Do you expect some part of your results to be affected by polydisperse effects? Because I mean, for example, the volume excluding effect, how would you expect it to change?
So let's look at the results. Essentially, the precise value of the viscosity would depend on the size distribution. So that would change. And for lower volume fractions, there is no issue with crystallization, but at higher volume fractions, if they crystallize, that would have a completely different behavior. So that would not be followed into the same category. But the difference is more quantitative, I think, and also more in the higher concentrations.
Okay.
No.
Okay, thanks. So let's see if there is, Jim, go ahead, just mute your mic.
That was a very nice presentation. I enjoyed it a lot. Thank you. I just was wondering, why is there no frequency dependence? If I understood correctly, you said there's frequency dependence with attracting particles, but no frequency dependence when the particles are repulsive. Why is that? What's the fundamental reason for that?
Yes, so it's a very good question. Maybe I can go to the slide. I put the statement there. So essentially, when you have a suspension in no Reynolds number flows, if the suspension can be approximated as hard spheres, the only time scale are the shear rate, because the repulsion is activated only when the particle overlap. Okay. So everything should scale linearly with the shear rate. There's no second time scale that would give rise to a rate dependence. We have to introduce an attraction force with a characteristic strength, and then you get a second time scale, and that gives the rate dependence.
But why does it work for, why is the rate dependence with attracting particles but not repulsive particles? What's the fundamental? I mean, I missed something that you answered it in what you said, but I missed what the connection is.
Yeah. So for repulsive, if you add a non-hydrodynamic repulsive force, theoretically there should also be a rate dependence, but people try to minimize that as much as they can. So make the repulsive force very short range and very strong, only at the near contact. So we want to minimize that effect. But if you also have a long-range repulsive force, there's no reason it shouldn't give rise to a rate dependence.
But it's very weak, I gather, from what you're saying.
Yeah.
Okay,
The collision force that dominates the excluded volume interactions.
right. Okay, thanks. I get it. Thanks.
Thanks for the question.
Okay, so let's see if there are other questions from the audience. Just once again, feel free to unmute your mic, or you can write in the chat and I can report the question. See in the chat. Okay, so I can ask you another question as well.
Go ahead.
In case you you include, let's say, longer range, actually, like lubrication forces, technically speaking, they are supposed to have a, not lubrication force, viscous forces, viscous repulsion is supposed to have an infinite scale, but it decays very fast. Yeah? So how does the decaying of how do you expect actually the decaying of viscous forces to kind of compare with the decaying of van der Waals forces, and how does this different decaying is supposed to play a role when you include the two of them?
Oh, yeah, that's a good question. Go there. So I think it's in the setup. So, so the van der Waals force, or physically, is an extremely short range force. Basically, it depends on the size of your particle. For non-collider particles, it's extremely short range. It should really activate it only when the particles are almost in touch. But so in that case, then it doesn't really matter. It's a very weak force, only happens at contact. In comparison to the hydrodynamic force, which are long range, you can feel that over tens of particle radius. But if you reduce the size of the particles, there's no reason to expect that still to be the case. Because even the non-hydrodynamic interactions would be a long range one, which would couple the dynamics. And also in that regime, you have to include Brownian motion, which would further complicate the dynamics. So in that case, the dynamics would be much more complex, I think. But I tend to think that the two mechanisms, one due to excluded volume interactions, the other attractive force, should hold. But maybe they would not be so separated as we see right now in this non-Brownian suspension case. Maybe they would more overlap and become more complex, but this is my intuition. I don't really know.
Okay. Yeah, well, that's the point you raised, that's somehow trying to characterize the neighborhood where this forces may this range kind of may turn to be compatible, and the fact that Brownian motion should be included. Yeah, definitely, that's a very interesting point actually, and evidently the phase space becomes quite more complicated just because you have multiple scales at play, right?
Yeah, and I think even experimentally they want to minimize these forces to do index matching and many other things to make a clean experimental system.
Okay, and by the way, the experiments you compare with, they are like they try to have monodisperse bits, or
yeah,
they okay, so you just have like an experimental deviation from the mean. Yeah,
exactly. So I think you were referring to this plot, right? This is experiments.
Yeah.
So it's a qualitative agreement. You need to tune the false profiles to match them, which we didn't do.
Okay. Yeah, sure. But, I mean, the comparison is very insightful in any case. Okay, thanks. So let's see if there are other questions from the audience, just to make sure that everyone has the chance to ask a question. well, that doesn't seem to be the case. Thank you once again, Anthony, for the very interesting talk, and it was very clear, and you entered in so many details of the physics. That was very interesting. So thanks for having accepted the invitation and for the seminar.
Thank you for inviting me, and thank you for including a Norrand's number talk. Maybe it was quite different. Thanks.
And, thank you. And then I wish you a good evening to everyone. And I remind you that this is the last session of the semester, and we will restart the seminar, the LMFL fluid mechanics webinars, probably in September. So thank you for attending the seminars, and to the speakers for having given us, for having shared with us such an interesting research. Thank you once again, Anthony, and have a good evening to everyone.
Thank you, everyone. Thank you for coming.